First, I would like to thank the organizers for inviting me and for setting up this interesting workshop. I learned a lot yesterday. I discussed so much that my voice is a bit attacked. I hope that you hear me. Okay, so I will be presenting the work that we carried out at the University of Mainz and now at the Vienna University of Technology on trapping and interfacing neutral atoms using optical nanofibers. And if you like, this work could be called nano-quantum optics. And maybe I first give a motivation on why we do this. The goal of what we do is actually to control the interaction between light and matter using integrated nano devices. And this is motivated by some immediate goals and applications in research and technology, because you could use these devices as sensors, as filters, as switches for nonlinear applications, cavity quantum electrodynamics, and so on. On a more longer time scale, you could also think about using these devices for combining the existing optical technologies with quantum physics in order to implement tasks in quantum communication, quantum information processing. And so the task we have to tackle now is to find suitable nano devices for interfacing light and matter. And of course, it would be great if they were directly linked to optical fibers. And what I will be showing you in my talk is that this task can actually be carried out using optical fibers themselves. Of course, at a first glance, using optical fibers for coupling light and matter seems like a bad idea, because optical fibers are made to protect light from the environment. So in a standard optical fiber, light is guided by total internal reflection in the core of the fiber. The cladding has a lower refractive index, and so the light goes on over large distances without being coupled to anything. And the trick now we play is to narrow down a standard optical fiber. And if you do this, then the core of the fiber gets narrower and narrower, and at some point can no longer guide the light. So the light now gets to the surface, and here in this region, in a sense, you have a new optical fiber, where the old cladding is now the core of the fiber, and the surrounding medium, like vacuum or some aqueous solution, is the cladding of the fiber. And at the surface, you can now couple the light that is guided in this silica wire with the matter that is surrounding the fiber. With this, let me come to the overview. I will present these optical nanofibers to you, their properties and how we make them, and I will then show you that you can use such optical fibers to trap neutral atoms. I will show you how these trapping potentials are realized, and also experimental realization and some experiments using this device. So if a fiber gets thinner than the wavelength of the light that it is guiding, then this ray path picture that I was showing in the beginning of my talk is of course no longer valid, and you have to remember that light is a wave and solve Maxwell's equations. And what you then find is that the mode that is guided by a sub-wavelength diameter fiber actually is not confined at the inside only, but has a strong pronounced evanescent field surrounding the fiber. Typical values in the case of our fibers is that the diameter is about half of the wavelength, and in this case you have about half of the optical power in the form of an evanescent wave surrounding the fiber. Okay. And this gives a strong lateral confinement, so it's like focusing the light and you have access to the light field. So this sounds great, but the question is, how can you get light into such a very thin fiber? You can't just use standard fiber coupling optics because this here is on the order of lambda squared. And so actually there's a very easy and convenient way to couple light in these nanofibers, and it is to realize these nanofibers as the waist of a standard optical fiber. So here you have in the beginning a single mode fiber, and the mode is guided in the core with a diameter of, say, 4, 5, 6 micrometers. And then you narrow down the fiber and adiabatically transform this fiber guided mode here into this cladding guided mode. And if you do this narrowing down correctly, and well, we do call correctly adiabatically, even if Tommaso will now maybe suggests to do this in a different way, but if you do it adiabatically, then experimentally we reach up to 99% transmission through the whole structure, so from here to here, which is a quite good number if you think about what brutal things happen to the light. So you squeeze this light into this very thin wire, and it comes out at the other side, and actually at the other side the core sort of sucks up the light field again, and it exits the fiber again in the fundamental mode of the single mode fiber. So we make such fibers by flame heating standard optical fibers and just pulling them with a computer-controlled fiber pulling rig, which is home built. And the important part is that we have an algorithm that is able to a priori predict what the tables have to do if you want to realize a certain fiber profile. So we tell the computer, I would like to have this and that shape of narrowing down the fiber, and out comes a fiber that very precisely meets these preset radius profiles. So just to show you an example, this is the preset radius profile, this black line here, for a fiber that is narrowed down to 320 nanometer diameter, and the red dots here are electron microscope measurements of the radius of the fiber, and the a priori precision of the fabrication process is so good that you hit the target diameter with a precision of a few percent at all scales. It's actually 3 orders of magnitude of narrowing down the fiber. Okay, and just to give you a visual impression, if this is an electron microscope image of a human hair, then such a nanofiber has the width of this PowerPoint line. This is actually not a thin fiber. Okay, so it's 100 times thinner than a human hair. Okay, so you could ask now, why is it so advantageous to use these fibers for coupling light and matter? And there, I would like to show you another cartoon which actually shows the scales. So if this is the fiber here, okay, which sticks out of the board now, and the red shaded area is the mode guided by the fiber, then this gray shaded disk is the interaction cross-section for a single 2-level atom absorbing this light, so which is actually 3 lambda squared over 2 pi. So you see that already a single atom should have, because it is sort of the shadow cast by the atom, already a single atom should have a significant effect on the transmission of light through the fiber. Okay? So, but in order for this picture to be correct, you would need the atom to behave as if it was in free space, because this 3 lambda squared over 2 pi is the radiative interaction cross-section. So in particular, you would need to keep this atom away from the surface, because if it was absorbed on the surface, it would be heavily perturbed, it would undergo much, it would be quenched much faster, and so this interaction cross-section would be much, much smaller. So what you would like to have is, say, this atom at 100 or 200 nanometers from the surface, where it does not see van der Waals interaction anymore, and still is close enough to the fiber to absorb the light field guided through the fiber via the evanescent field. And what I will be showing you now is that this is actually possible. We can pin down the atom at 200 nanometers from the fiber using the light field guided in the fiber itself. Okay? So the idea is to use detuned light fields, and detuned light fields will exert dipole forces onto the atom. And the idea is that if you have a red detuned with respect to the atomic transition, a red detuned light field in the fiber, then atoms which are polarizable will then be attracted to the high intensity regions, and meaning that they will be accelerated towards the fiber. But this is not all you want, because this would mean that you would eventually hit the fiber and the atom would then absorb on the fiber or just be heated away. But the trick we play is that in addition we send a blue detuned light field through the fiber. Now the blue detuned light field does the opposite. It repels the atoms from the fiber. But the decay length of the evanescent field is proportional to the wavelength, and the blue light has a shorter wavelength, so it's more tightly confined to the fiber. This means that if an atom approaches the fiber from a distance, it will first see the red detuned field, so be attracted towards the fiber, and then it sees the repulsive blue field and it's repelled, meaning that at a distance that we can set by choosing the detunings and powers, we can have a stable trapping minimum. So here you see the red attractive potential, the blue repulsive, and here at 200 nanometers from the fiber, we can have a trapping minimum of about 400 microkelvin depth. Okay. Now, this shows you that it's possible to trap atoms in the radial direction, but we would actually like to pin down the atoms in all 3 dimensions of space. We would really like to hold it at one position along the fiber. So in the axial direction, this is easy, because all we need to do is to send the red detuned light field from both sides. Then we get a standing wave, so the attractive red potential has a sinusoidal intensity modulation along the fiber, and the atom will be trapped along the fiber. So this is shown here, so this is the fiber surface, and on each side you see this periodic now trapping minima, which are actually spaced by half of the wavelength in the fiber, so in our case about half a micrometer. Now this still seems to indicate that now we have a toroidal trap, okay, because we have radial and axial trapping, and this is true. We can realize toroidal traps around the fiber with this method. If we would in addition like to have azimuthal confinement, so in this direction, then we need to play a trick which is not so well known maybe, which is we make use of the fact that the intensity distribution of the evanescent field around such a fiber is not azimuthally symmetric if the light field is linearly polarized. This is in general true, but usually in normal optical fibers you don't see this effect because the index of refraction jump is very small. But here we have a huge, 0.5 index of refraction jump, and in this case, if I have the fiber like this and light polarized like this, I have more light here and less evanescent light here. So if we send the red detuned light field linearly polarized like this and the repulsive blue like this, then we have more attractive light here, more repulsive light here, so we also get azimuthal confinement of the atom. So the overall view of the trapping potential we then realize is shown here. Here everything is to scale, so this is a 500 nanometer diameter fiber, and what is shown are equipotential surfaces 40 microkelvin and 125 microkelvin above the trapping minimum. And what we obtain is a one-dimensional optical lattice above and below the fiber. Okay? Now we can load atoms into this trap just in the same way that you would load a standard dipole trap, meaning that you can use a magneto-optical trap, just send, if you have laser beams, the laser beam through the mod and transfer the atoms from the magneto-optical trap into the dipole trap. Here we do the same, but what we need to do for this purpose is to stick the fiber through the cloud of laser-cooled atoms. And actually the magneto-optical trap that we use still works fine because the fiber is so thin that the atoms just don't collide with it. So we have a normally operating mod, and we can run a sequence for loading the atoms in the trap, which is standard for loading a dipole trap. So I don't talk about this anymore, but I immediately go to what you do then with the atoms which are loaded into the trap. So in the experiment we use cesium atoms. So in this case, the resonant wavelength is at 852 nanometers. And what we use as a red detuned laser is a neodymium laser with a power of about 2 times 2 milliwatts that we send from both sides into the fiber. And for the blue repulsive light, we use a diode laser at 780 nanometers with a power of about 25 milliwatts. With these parameters, we realize a trap depth of about 400 microkelvin, which is just the potential trace I showed in the plot in the beginning. So this is the experimental parameters here that you need to realize it. And in order now to see that atoms are actually trapped in this trap, we just need to send a faint resonant probe laser through the fiber, because this resonant probe laser now also couples to the atoms via the evanescent field, so the atoms will absorb this probe light and fluoresce. And we can simply look at the fiber while sending the probe laser through the fiber. And if we look at the fiber using a very sensitive photon counting camera, then we can in situ see the fluorescence of atoms trapped on the fiber. Now this is trapped atoms which are fluorescing. The length of the fluorescing ensemble of atoms here is about a millimeter or between half a millimeter and a millimeter, which is just the size of the cloud of the magneto-optical trap. So we load atoms into the trap where the mod operates. What you have to believe me for the moment is that this is actually 2,000 atoms, which are trapped, as I showed you, 200 nanometers above the fiber. And another thing that you have to believe me right now is that actually this is at most 1 atom per potential well, meaning we cannot have more than 1 atom because the potential well is so small that as soon as a second atom enters the trap in the presence of the near resonant light of the cooling lasers, there is a light-induced collision that Stefan Kuhr also presented on the first day that he uses to project onto modulo 2, the atom number. And in our case, this effect saturates, so we have 0 or 1 atom at each potential well arbitrarily. So this is kind of random, but still some non-Poissonian statistics. And maybe one last remark. So this is atoms 200 nanometers above the fiber, and the temperature of these atoms, we measured it, is about 30 microkelvins. So the ratio of temperatures, imagine the fiber itself is 300 Kelvin hot, and we have 30 microkelvin cold atoms, and they don't couple to this hot surface, and the ratio is just the same as if you took a snowball and you sticked it into the center of the sun, and it does not melt, okay? So it's 7 orders of magnitude difference in temperature. So, of course, just looking at this is kind of qualitative. I mean, we can do quantitative analysis of these signals, but which is a much more quantitative way of measuring how the atoms feel in our trap is, instead of looking at the fluorescence, looking at the transmission of this laser, because if the atoms scatter light, then it should be missing here. And scanning the laser over the resonance and doing spectroscopy of the atoms in the trap. And if you do this, then you see that these 2,000 atoms actually yield a totally optically dense ensemble of atoms. So here you see the transmission through the fiber as a function of the tuning of the probe laser, and you see that over several 10 megahertz there's just no transmission at all because it's just optically dense. And you can compute the optical density just fitting the data here, and what you find is that we have an optical depth of about 32, so e to the minus 32 transmission through the fiber, which means that we have about 1.6% absorption per atom. Okay, so this is really a good number for a single atom. Now, of course, this way of probing the atoms is destructive because you scatter photons, and this means that you will heat up the atoms, and eventually the atoms, while probing, will eventually leave the trap. But it's also possible to gently just, probe the atoms by using a dispersive probing scheme. This dispersive scheme now uses a probe which is detuned. And if you have a detuned probe, then all the atoms can do to this light field is impart a phase onto the light field propagating to the fiber. And you can now detect the presence of the atom by detecting the phase of the light field. For this, you would usually need an interferometric setup, and this is complicated because you have to stabilize it and so on. But the way we detect this phase is, it's also interferometric, but the interferometer uses not 2 different spatial modes like in a Mach-10 interferometer, but actually it uses 2 polarization modes. The idea being the following: if the atoms are trapped above and below the fiber, and I use linearly polarized probe light, which is linearly polarized like this, it couples more strongly to the atoms than if the linearly polarized probe light has its polarization axis horizontal, because there's more intensity at the atoms in this configuration than in this configuration. The factor being about 2.8 in the coupling strength. This means that this polarization will pick up a phase which is 2.8 times larger than for this polarization. So then you can measure the phase difference between these 2 polarization modes. And how do you do this? It's very easy. You just send a linear superposition of these 2 modes, which is just linearly polarized light at 45 degrees. Now this contains this polarization and this polarization component, and if I now have a retardation of this polarization component, it will just result in the polarization turning and becoming elliptical and eventually circular. So if you look at the Stokes vector of the light propagating through the fiber, then as a function of this phase difference between the two modes, okay, you see the linear component disappearing while the circular component appears. So if you measure this S3 component, so it's actually the circular component of the light, as a function of laser detuning, you can map and you can measure this difference of phases here for the light. So this is easily done. You just, after the fiber, put a quarter wave plate, so you convert the circular polarized light into linear polarized light, and you look at the two components, sigma plus and sigma minus here, and then the S3 component is just the difference of the signals of the two photodiodes here, okay? So if you plot this and compute the phase, the different imparted onto the strongly coupled polarization axis as a function of laser detuning, you see this nice dispersive shape that you would expect from the atoms interacting with, from the light interacting with the atoms which have a resonance about here. So in this case, we were working with 1,000 atoms, and again, this plot yields an optical depth here on the order of 30, which means that we have an effective far detuned on resonance optical depth of 2.8% per atoms in this case, or a phase shift per atom of 2 degrees times megahertz. I mean, you have to multiply this by the, or you have to divide this by the detuning. So say if you have 10 megahertz detuning, then you have 0.2 degrees phase shift per atom. So this is really significant effect, and you can now use this phase shift to non-destructively detect the atoms. So we have shown this here in this plot, where you see that the number of atoms as a function of time after trap loading is the same for both probing methods. So it's actually exponential decay of the number of atoms with a decay time of about 50 milliseconds. And if we use this absorptive method here, so just looking at the absorption of light, then what we do is we load the trap, then we wait, we do nothing, and then we send a laser pulse and look at the absorption. So all the blue dots are actually single measurements with one ensemble of atoms, whereas this red line here is actually a single trace of one and the same ensemble of atoms that has been continuously probed with a dispersive method, and you see that the decay constant is about the same. Okay, so with this, I would like to summarize. I've presented these nanofibers to you and then shown you that you can use these nanofibers to trap atoms. The atoms are trapped in a one-dimensional array of trapping minima and yield a totally optically dense ensemble on the order of 2% absorption per atom. And it's also possible to dispersively detect the atoms using a detuned probe. So with this, I would like to come to the outlook, where I would like to go a bit into the direction of this workshop, which was quantum correlations in many-body systems. But maybe first, to put it in a nutshell, what you've seen so far, it's really that atoms become a fiber optical component in a sense, because it's really these tapered fibers come out of our vacuum chamber, through a feed-through, and are then normal standard optical fibers on the table. So every laser that you couple into these fibers directly couples to the atoms which are trapped on the fiber. No alignment or whatever has to be carried out, because everything couples via the evanescent field to the atoms. Okay, so when it comes to many-body physics, then there are different approaches that you could take. First of all, what you could look at is actually light meta-quasi-particles. And one way of generating such so-called polaritons is to use electromagnetically induced transparency, so a 3-level lambda scheme, and you shine in a strong coupling light field on one of the two transitions, and then actually on the other transition you can send a weak quantum field that couples, and you can then coherently prepare the ensemble in such a way that the excitation caused by this quantum light field behaves as a quasi-particle. And if you send the control field from both sides and generate a standing wave of the control field, then you can actually generate, in a sense, spatially modulated susceptibility. And if in addition the quantum field not only couples in a 3-level scheme, but you have in addition fourth level here, and the quantum field also couples to this fourth level, then you can have a Kerr effect where you have an interaction between the photons, between two photons of the quantum field via the shift imparted onto this level here via the Kerr effect. And if you play everything right, then you can actually show that the dynamics of these so-called dark state polaritons is exactly mapped by a nonlinear Schrödinger equation where you can set the effective mass and also the interaction strength between the particles by the detuning and the coupling strength of the classical light fields. Okay? And for this system in 1D, it has been predicted, Giovanna is one of the authors, that these quasi-particles can actually crystallize. Okay? So you can have an interaction, you store photons in the form of dark state polaritons, then they crystallize, and you could then transform them into photons again and map them out and see that you should have like a chain of photons coming out. And in that sense, the dark state polariton physics you can do in this system is bosonic many-body physics with variable interactions. But if you look at the theory proposed, and I think in this paper, the good physics starts when the optical depth of the sample was on the order of 1,000. And when I first saw this proposal, sorry, but I was just laughing. Because 1,000 is tough. I mean, it's really, we have 30, okay? But now I'm no longer laughing, because there's one way of cranking up the coupling of light and matter. For the experiments I've showed you, the light was just passing single pass through the ensemble. Okay? It was just a propagating mode. But I can recycle the light by putting mirrors around the ensemble and just making the light go back and forth through the ensemble several times. Now, in order to realize this, what we did is to just put a so-called fiber Bragg rating into the unprocessed fiber ends of our tapered optical fibers. So this is just, in a sense, a mirror, okay, that you put here. And now the light bounces back and forth between these two mirrors. And since in our fibers we're able to have extremely low loss transmission through this taper, we can still have a reasonable finesse of this. It's a Fabry-Perot resonator, and we can still have a reasonable finesse of about 100, okay? Which shows you that the transmission through our tapered optical fiber in this case was actually 98.3%. It's very precisely determined by this method, by just measuring the finesse before and after tapering the fiber. And the interesting thing now, or the interesting number, is that the single atom cooperativity, so the ratio of coupling strength of the atom to the light field to the decay rate of the light field and the atom, is about 30 for a single atom, okay? So if you just plug in the numbers for cesium atoms, you would expect these parameters, so here 33 megahertz for the light atom coupling strength. The line width is about 10 megahertz, while the decay rate is about 2.6 megahertz for the dipole of the atom. And now if you look at this finesse, then you know that actually the light goes around about 100 times before it leaves the cavity. This means, and actually the exact calculation tells you that if you have some optical depth inside the cavity, you have to multiply it by the finesse divided by pi. So in this case, you just multiply the optical depth of 30 that we could realize so far by the finesse divided by pi, and you end up with about an OD of 1,000 for 2,000 atoms. And in addition, this resonator here, it can be combined with our atom trapping scheme, because these mirrors here are very narrow band and they just reflect light at the resonant wavelength, while the trapping light can just pass through and does not see the mirrors. So we can, in principle, combine this. This is something we would like to realize in the next future. And one last point that I would like to mention, the other way of doing many particle physics in these traps would be to just put a BEC into the trap, okay? And there are actually, I mean, this would be a one-dimensional optical lattice, so you could maybe do Mott insulator and so on, but there's also trapping geometries which are not so easily realized with freely propagating laser beams. I mean, a 1D optical lattice can be realized just by interfering laser beams, but let me show you what cannot be easily done with laser beams. So I told you that the we make use of the fact that linear polarization leads to a breaking of the azimuthal symmetry. Okay? So if we have linearly polarized red detuned light, then we can trap the atoms, say, here and here. And now imagine that instead of the configuration I've shown you in the beginning of the talk, we send the red detuned light from both sides, but with sigma plus and sigma minus polarization. Okay? Sigma plus plus sigma minus is also linear. Everybody knows this. But the direction of the linear polarization depends on the phase of sigma plus and sigma minus. So sigma plus plus sigma minus is like this. Sigma plus minus sigma minus will be like this. And the phase between these two fields, of course, depends on the position along the fiber. And it means that the linear polarization spirals while you go along this fiber. If the blue detuned light at the same time is just a running wave which is circularly polarized, it has this azimuthal symmetry. So this means that you get a trapping minimum here and here, but then if you go along the fiber, the whole thing should twist. Okay? And if you plot this in 3D, you see that you got a double helix potential. Okay? So double helix potential is almost a nature title on its own. And now the interesting thing is that you can think of loading a Bose-Einstein condensate into these waveguides. So you have one-dimensional waveguides which are curved in space. Okay? And here really interesting things can happen. If you have some, for example, a long-range interaction like dipole-dipole, then there is while dipole-dipole is always repulsive if the two dipoles are like this, if they are on a helix, then here they repel because they're next to each other, and after one turn, they're like this. And they attract. So you see that the monotonous dipole-dipole interaction is turned into something that has a trap that has a minimum depending on the distance along the helix. Okay? And so this is quite interesting. And at the same time, what we can also do, which is something that you cannot do with laser beams neither, is that we can vary the helix parameters locally by varying the diameter of the fiber. So if you just use the right detunings and wavelengths and so on, what you can show is that if you vary the radius, so here's a radius of 250 nanometers, and now we vary it by plus minus 10% here. So this is the radius of the fiber, it's like the radius profile. And if you vary it over, say, 50 micrometers here, then the position of the trapping minimum or the radius of the helix does the opposite. Okay? So you can have a hump of the helix on the fiber on a length scale of, say, 50 micrometers. And this, again, is interesting because that leads to bound states on its own right. Okay? It's a purely quantum mechanical effect, but you can have geometrically bound states and such humps on a helix. So we think that there's quite some possibilities of doing many-body physics in such a trap. So with this, let me thank the people that worked on the experiments, the old PhD student, Eugen Fetsch, and the postdoc Sam Dawkins, and now we have Daniel Reitz and Rudi Mitsch as PhDs, and Philipp Schneeweiss as senior scientist. And thank you to the funding agencies and you for your attention.